All right. So looking at the announcements, I think that I've already told you the research paper is optional, and in fact, just to afford you maximum flexibility, if you want to submit that, you can do so as late as 9 a.m. on Friday of this week. So that's the research paper. Your last homework assignment having to do with watershed modeling is due on Friday, and that assignment includes some of the stochastic modeling tools that we talked about in class last Friday, but it does not include any HEC-HMS, which we're going to be addressing today. In fact, neither will the exam. The HEC-HMS is just mainly for your reference, and it's kind of local importance because the Army Corps of Engineers has an office here in Huntington, so I think it's important to address that model since it was developed by the Army Corps of Engineers. But it won't be on the test, and it's not in the homework, so take that for what you will. Speaking of the final exam, that is on Friday the 1st of May. We'll have a 2-hour window, and unlike the midterm exam, I'm not going to email it to you. It'll just magically appear on Blackboard at 8 a.m. And so I may send you an email reminder that the exam's at 8, but you'll access the exam on Blackboard and you'll submit it on Blackboard. So it will be open and available for you to see and submit during that 2-hour window. The final exam's comprehensive, meaning that I may ask questions from at any point during the semester. The rationale from that is that hydrology is naturally a topic that kind of builds on itself, and it's sequential from the foundation upward, so it would be really difficult, if not impossible, to ask questions that had no relationship to the earlier material. Now that said, a disproportionate number of the points will be taken from questions that address topics since the last midterm exam. And so that means you can expect a disproportionate number of the points to come from the most recent watershed modeling stuff with WMS, since that's what you've done since the last midterm exam. It's going to be the same ground rules as the previous midterm, where you can use your textbook, you can use your notes, you can use previous homework assignments, any kind of written or print resource that you like. But what you're not allowed to do during the exam is collaborate with another student or any other people. So it should just be solely your effort that's submitted. And then finally, be prepared for questions that include an HY8 problem, something where you'd need to use Excel or StormCAD. So all that software you need to have at the ready in case the questions cover those topics. Any questions about the announcements before we start talking about HEC-HMS? I see a question here from Jeffrey. He asks, how would you like us to submit the HY8, WMS, and StormCAD files? Compressed zip files. Yeah, that's what you need to do. Since, well, HY8 usually would submit that information as a screenshot. But the WMS and StormCAD, since it creates multiple files rather than upload them individually, it's better to zip them. Any other questions before we move on? All right, so we're talking about HEC-HMS today, and a lot of people think of HEC-HMS as the replacement for HEC-1. I think it's maybe more accurate to say that they've developed in parallel since HEC-HMS was introduced for the first time in 1992. And one of the motivating factors for introducing HEC-HMS is that HEC-1 was written originally in an old computer programming language. I think it was Fortran at the time. And it did not have a visual environment, which meant that if you were a modeler setting up a HEC-1 simulation of a watershed, what you had to do was create these text files as inputs, and then HEC-1 would read those text files that you'd prepared and then export additional text files that you could maybe create your own hydrograph with. And so we've been using WMS as our pre-processor and post-processor, but when HEC-1 was first introduced, WMS didn't exist, and so people had to set all of that up manually. So the thinking was with HEC-HMS was they could introduce a new program that had a few new developments on the hydrology side, as well as a graphical user interface that would make it much easier and quick to set up watershed models. And so that's what they did with HEC-HMS. My personal impression is that the GUI that they introduced isn't quite as user-friendly as WMS, and it certainly isn't as feature-rich. And so specifically, the new features that it introduced was a distributed runoff transform called Mod Clark. And what that allows you to do is simulate the the spatial distribution of runoff over the course of a watershed in a more sophisticated way than, say, the SCS method, where you'd be calculating the time of concentration. And so it is a genuine improvement in the hydrology, but the issue is that, at least in my impression, it's rarely used. There may be some sophisticated kind of niche research applications where Mod Clark has been utilized, but I personally don't know any modelers who use it on a routine basis for the type of projects where you'd be, quickly going through a series of watersheds, trying to figure out the peak flow rate, sizing culverts. And so it's maybe more of a specialty application than a routine everyday use kind of model feature. And the same thing is true of the new capability to do continuous simulation of soil moisture. We don't normally have a good understanding of precisely what's the soil moisture at the beginning of a simulation. And so if we don't have that boundary condition, then we can't set up a model that's predicting the soil moisture. So, if you went into the field and you measured the soil moisture, or if maybe you have satellite data that's estimating what the soil moisture is, you could use some of these new features, but in most of the situations it either wouldn't apply or you just don't have the data to use the new features. And so in summary, HEC-HMS has new features that are rarely used. At least I've rarely used them. And so that's the advantage. The disadvantage is that HEC-HMS doesn't offer the same capability to automatically obtain GIS data like WMS can. And so WMS is used to set up HEC-1 models or to set up HEC-HMS models, and it will go to the websites that host the digital elevation model that you need, that host the soil type and land use data. So it does the dirty work for you of going and getting your underlying GIS data, and HEC-HMS won't do that. It can read some GIS data, but you have to track it down yourself, and that's time consuming. It doesn't offer also the same flexibility in delineating watersheds as WMS does, and it doesn't offer quite the same streamlined parameter computation tools. And so I continue to believe that WMS is a superior way to set up watershed models. You can use WMS to set up HEC-HMS or HEC-1, but in the end, if you're not using any of these new features, it doesn't matter whether you set up a HEC-1 or a HEC-HMS model, because you get the same runoff value. It uses the same calculations, like the math that's going on in the background is the same. It's just that the model was programmed in a different language. One thing about what WMS can't do is it can't run the HEC-HMS model inside of WMS. All you can do is set up the input files, and then you have to go outside of WMS to run the HEC-HMS model. And so that's what we'll do today. Is we're going to look at a watershed, find out the HEC-1 runoff value, just so that we can prove to ourselves that we'll get the same runoff hydrograph in both cases. So we're going to, with the same watershed, set up a HEC-1 and a HEC-HMS watershed. So any questions so far before we start into that activity of delineating the watershed and finding the peak runoffs? Okay, we're going to look at a different type of watershed than the ones we've been looking at here in Cabell County. We're going to go into the central part of the state, and there is a watershed that's just immediately to the west of Canaan Valley State Park. And it has, unusual, well, has different geology than what we see here in Cabell County, and so the watershed shape will be a little bit different than we're accustomed to, but that's what we're going to do. And so it's in Davis, West Virginia, and let's start WMS in Davis, West Virginia. Alright, so we'll begin the wizard and save a project file. And be sure to click the Save button, and let me help you find our project location. Be sure that you have your projection defined, and then for the boundary we'll type in Davis, West Virginia, and jump to the location. And so Canaan Valley State Park is south of Davis, and so if we zoom out a little bit and pan downward along Highway 32, there you can see Canaan Valley State Park, and then here is the South Fork of the Red Run. In the center of the screen there you can see the South Fork of the Red Run. And so you can begin to get a feel for what the boundaries of that are. Here is the southernmost tip of the watershed. Here is its boundary along the east. Here's the ridge line along the west. And so we can zoom in a little bit, and what we'd like to delineate is what's the watershed's contributing area where the South Fork and the North Fork join together. What is the location? So the locations start with Davis, West Virginia, and jump to that location, pan to the south, and here is the state park. So what we're looking at is south of Davis, and here is the South Fork of the Red Run. And so zoom in so that you've got this same view on the screen. So at this kind of zoom level, it's going to automatically suggest the 15-meter resolution, which will give us a good balance between resolution and not getting too much underlying data. If you have the union point in the center of the screen, then you won't get the whole watershed. So we just want to see where the North Fork and the South Fork come together. So this view will look good for us. Alright, so when you have that as the bounds, then you can click OK. Alright, so you can see the coordinates, and I mean, if you really aren't sure about the location, you can type in the coordinates directly that I have. Let me know if I need to come back to those. But click Next. We're going to use the web services and get the elevation data, land cover, and Surgo soil type. And here we'll use the 15-meter resolution DEM. So click OK, and then it'll prompt you for the land cover, 20 standard, the 20-meter resolution for that, and then it will also go through the big job of getting the soil type. I think it's going to trigger a couple of adjacent counties that we don't need the data for, so we'll be sure and delete those as soon as it goes through and finishes getting all of the data. It's reading it in. Alright. I'll wait a moment in case your soil data is also still in the process of downloading. Okay, the bottom two on the list are data sets that we don't need. So I'm just going to immediately remove those by right-clicking on them and clicking delete. Okay, so they're gone. I'm going to turn this off for now, turning off just so that I can look at, I'll also turn off the elevation and the land cover. Alright, right away things look a little bit different than we're accustomed to from the elevation map. And let's go ahead and start the wizard back up again and skip to topaz. So compute topaz, and it's going to find where the flow accumulation cells are. So those blue lines will come up, and it's hard for us to right away know which is the location that we're interested in, because in the past what we've used as visual clues was the curvature of the river, and here things are kind of flat. So what I suggest we do is turn on a map in the background, and since this is a really wilderness area, the street map wouldn't do us the same favors that it often does when we're working like alongside a highway. Instead of using the street map, I suggest that we'll use the world topo map. So where you turn on the world topo map, then in the background, here we go. We can see here's the South Fork, and it's where it's joining just right at the boundary, the North Fork. So we're going to drop our watershed outlet here in this location, just where the, if I turn off, it's where this road is meeting the South Fork. Alright, so bringing the wizard back again to the forefront. Oh, by the way, maybe as soon as I delineate the watershed, I'm going to save again. Alright, so create outlet, and put the outlet just prior to the union of the North and the South Fork. Okay, so you can see where I've dropped the outlet, and then delineate the watershed. Alright. Now, in the past, we've been using like flat lines as an indicator that maybe we haven't zoomed out far enough to get all of our watershed data. And here we don't have any flat lines. We have the entire watershed, but the boundaries of the watershed are parallel, and that's because of the underlying geology of the area. So it may seem that it's coming to a point like this, but it comes to a point because that's kind of a singular hill, a big plateau in the area, and our ridgeline goes through it. So here's our watershed, and it's almost exactly 1,000 acres. So hopefully you have a similar watershed area. And we're going to use this to calculate a HEC-1 and then set up a HEC-HMS and execute HEC-HMS and see if we get the similar values for both. So we have to go through the process of calculating our curve number and setting up the HEC-1 model just to have our baseline understanding. By the way, I'm going to save right now, so click on the save button just to make sure if things crash we could come back to this point. So starting the wizard back up again, we've already delineated the watershed. Click next, select model, so initialize model data with HEC-1. We'll do the HEC-1 first, and then we'll set up the HEC-HMS. Okay, so click next. Let's have the job control. Let's set it to be, it started on Friday at 12 p.m. noon, and it ended on Saturday at 12 p.m. noon. Okay. And 15-minute time interval. So set job control. Okay, so next we need to join NRCS, and we'll fill the blank values with the default soil group C. Okay, so we've joined NRCS. Now create the coverage, and you can see right now we only just have the drainage coverage, and when I click create coverage, then it copies the applicable polygons from the GIS file up into the coverage. And so go through this mini wizard here, click next, double check that it's going to be mapping out these hydrologic soil group. So click next and finish, and then we get prompted for we've got the soil type coverage is created. So click next and then compute GIS attributes. So it's using the soil type coverage that we just mapped for the soil type, the grid, which is the land cover database for the land use. We have to import our key that has the relationship between land use, soil type, and curve number. So browse to the location where you have this curve number text file. Okay, and then when you click OK, it gives you the prompt to open up the little report. And we have a much lower curve number here than we've seen in any of our Cabell County watersheds. It's because a good part of this watershed is soil group A. We have quite a large section of it, mixed forest soil group A with a curve number of 30. So more than 10% of the watershed has a curve number of 30 because it's mixed forest, and then another roughly 10% of the watershed has curve number 30 because it's evergreen forest. So that brings the average pretty low with a resulting curve number of 61. Okay, so we're doing stuff we've already done before. Let's compute the time of concentration with the basin data and use the SCS method to determine that our lag time is 1.06 hours, and then that copies it into the time of concentration with the 5/3 conversion. And click next. Let's define the precipitation, and it opens up now the HEC-1 window that sometimes we get to just by double clicking on the basin. Well, it popped it open for us, and we can see that the loss method has the curve number copied in that we've already determined, and the unit hydrograph has that same lag time that we've seen already. But what we can go to is the precipitation tab, use basin average, get precipitation. Let's do the 10-year storm for this location. So in the drop-down box, use the 10-year 24-hour storm and get data. It retrieves that from the NOAA Atlas 14. You can see the mean value of 3.7 inches. Okay, and now what we need to do is spread that out temporally. So we'll define the series with type 2 24-hour. Okay. So we've defined the precipitation. Click next. We don't need to clean up the model. It's clean. Alright, so we can click run simulation, and then it will do the same thing as if we'd been through the HEC-1 model menu at the top of the screen. So run the simulation, it ends, and then it automatically loads the hydrograph. So let's close the wizard. I'm going to turn off the soil type. I'm going to turn off the topo map. In fact, I'll even turn off the elevation data. And so now I'm just going to use this select hydrograph tool and double click on the hydrograph, and it brings it open here. It's shocking what a difference curve number makes. We kind of saw that in our class on Friday when we did the stochastic method, and we saw a huge spread between the low curve number runoffs and the high curve number runoffs. And so this is a 1,000-acre watershed, and what this is telling us is that in the 10-year storm we're only going to have 122 CFS. So we definitely have, for a 1,000-acre watershed in Cabell County, we'd have a much higher peak flow, partly because the curve number difference, but out here you may not have noticed, but the watershed slope is quite a bit lower as well. Let me just show you that briefly, that if we go here into the drainage module and select our basin, let me switch over to the drainage coverage. Okay, when you just click on the basin, then over on the right side in the properties, it says the BS, the basin slope, is only 0.1885, so 18% basin slope, And out here in Cabell County, I think like 30 at the minimum. You know, it's not uncommon to see basin slopes as high as 40%. And so part of the reason why we're seeing this low, let's switch back over to hydrologic modeling module, part of the reason why we're seeing such a low peak flow is because of the curve number, but it's also with less of a slope, that means the time of concentration is later, and when you delay the peak, you're also bringing it down. So there's definitely some similarities to you know, a runoff hydrograph and this flatten the curve notion that everybody's been talking about with the pandemic, that if you flatten the curve, you're taking the peak lower and you're shifting it so that it occurs later and creates less stress on the medical system. Well, the same thing is true with creating less stress and having a lower peak in a hydraulic system. Okay, so we've done HEC 1, but we'd already done that before. Let's try something new. Let's try setting up the HEC-HMS model. Before we do the HEC-HMS component, are there any questions, or does anybody need to see a certain thing again before we move forward? All right. Well, if not, let's save our work. Click on the Save button here. All right. So what we're going to do now is in this drop-down box, right now it's set to a HEC 1 model. Well, we can change it to HEC-HMS so that now if I select the basin and double-click, it brings up a new window that we haven't seen before, the HEC-HMS properties window. Let me make that a little bit bigger by dragging down here in the corner. Okay. So you can see that it's asking us for a loss rate. It's asking us to define what they're calling a transform, and then it's giving an option for base flow. So let's go through each one of those individually. First of all, loss rate is the options that HEC-HMS has for defining the rainfall runoff relationship. So in other words, how much rainfall will cause what amount of rainfall excess. And the approach that we've been taking so far has been the SCS curve number method, but that's not the only approach either in HEC 1 or in HEC-HMS. There's other models for estimating how much of the rainfall is going to be runoff. And I think we talked about the green amped method when we were going through the fundamentals and theory part of the course when we're talking about infiltration. So green amped method is one of the models that we've talked about. So if you turn on, so click the tick box here for loss rate method, that means that we're going to define a loss rate method, and the default that it's set to for our basin. So we can see that our basin that has an area of 1.5 square miles, it's set to the SCS curve number as the default. And that's not only because it's the most common, but we've already defined the curve number. And it will copy the data over. The calculations that we've done so far of getting that curve number of about 61, it'll paste that in there. So we've set a loss rate for our model. The transform is about defining the time of concentration. So it's not the amount of runoff, but the timing of it. So turn on the transform, and now with the transform, you can see the transform method is the SCS method, and we have other options for defining the timing of the rainfall. Not all of the same options that we're accustomed to seeing when we do a HEC 1 simulation, but many of them. And just to double check that it has the data that we need, we can go here into basin data, and it's showing the same lag time of 1.06 hours. And so that will be copied over when it creates the HEC-HMS file for us. Scrolling down a little bit further, base flow. A lot of streams have water in them before a storm comes through. And so, you know, if you drive around here, you may look into like the Mud River, the Guyandotte River, certainly the Ohio River. I mean, they have water in them all the time, whether or not it's been raining. And some of that is groundwater that's seeping into the stream. And so you can add a certain kind of base flow, as it's called, the amount of water that's in the channel before the storm occurs. We won't turn on the base flow because we don't know what would be a typical flow rate value through this particular creek, and what we want to do in this demo today is just compare it to the HEC-1 model that we've already run. So I'm going to leave the base flow turned off. Alright, so once you click OK, then here in the HEC-HMS model across the top, let's look at what options we have available. We have job control. Let's open that and just make sure that it's set correctly. The job control, we need to adjust that. We would get an error message right now. So let's set it to be, what did we say, Friday? No, last Friday. So Friday the 17th starting at noon. So 12 o'clock p.m. And this is actually pretty important, the timing of it. HEC-1, at least when it's run through WMS, it's pretty resilient. You don't have to put in the exact time that a simulation starts. You can just kind of let it figure out on its own, and it will. But HEC-HMS is a little bit more picky about when a job starts and that it's in even increments. And so, you know, we're starting exactly at noon and we're going to finish at exactly noon the next day. So on the 18th at noon, because it's looking for this time period to be divisible by the time interval that we've selected. So we're using a 15-minute time interval, and if your start and end time don't match up, you'll end up with an error message. So we're okay there. So click OK. Here in HEC-HMS, meteorological parameters wasn't defined when we were telling it the basin data. So when you double click this HMS properties box, it's only telling it about the basin properties, and it's not telling it yet about the precipitation. So we do that in a separate place. What we do here in the HEC-HMS drop-down window, we go into meteorological parameters, and it's copied over from before the 3.74 inches. But if it hadn't, you know, like if we'd gone straight to HEC-HMS instead of doing HEC-1 first, you could do download from web, and the same tool where it knows the location and we're getting a certain return period, and so it could have gotten the data for us in the same way that it always does. And then this button here, the XY, is the temporal distribution of the depth. So if you click on that, then you can verify that it's still set to type 2 24-hour, and then it has the XY editor over here on the left side that's defining this curve. So click OK. So we've defined the job control, which is the starting and the stopping of the simulation. We've defined the basin parameters, which is the area of the basin, its curve number, the time of concentration, that sort of information. And then in the meteorological parameters, we defined what would be the precipitation depth and its timing. What we can't do is we can't run simulation. You'll notice that that text is kind of grayed out. It's because it's not available to run it within WMS. HEC-1 was kind of a program that you can trigger from another program, but what we can do is save the HMS file. So do that. Click on Save HMS File, and then browse to a location that you're going to be able to find in just a moment. So I'm going to put it here in this subfolder I'm calling HEC-HMS class, and then I'm going to give it a subfolder that's called Export. Okay. Davis. So I'm calling my model Davis, and it'll take a moment to create all of the files that need to be there for HEC-HMS to be able to run. And let's just explore what WMS put into that directory. And so if you open up through your file manager the location, it was this export subfolder that I put things in. The main file that we are going to be opening up in HEC-HMS is a .dss file. But that's not the only one it's created. It's created all of the files that HEC-HMS needs in order to do this run. And so the run file name has the starting and stop time. The MET file name has the meteorological data, so the rainfall amount and the timing of it. The DSS is kind of like the main container file that has our boundaries, our watershed characteristics. And so I sent you the link to download HEC-HMS, and they have two different kinds of downloads available. You probably noticed that there was the portable file and the other one. So let me just bring that up for a second and show you why I suggested the portable. Alright, so here is the HEC-HMS download site. It's free software that you can get anytime you like. Now the portable, you can run HEC-HMS without actually installing it. When you install a program on your computer, it creates entries in the registry, and so if you think you're going to use it a lot, then you can use this installer version. But if you're just going to use it occasionally, or you don't have like user access, like sometimes you have to get the IT department to install software for you, you could run the portable version without that in many cases. So that's why I suggested the portable version. So go to wherever you have, here's the zip file you probably downloaded, and here is the HEC-HMS. What we're going to run is this executable. Okay, so double click on the executable and it will maybe give you a security error the first time. I mentioned that in my email last night, that just so few people run this program that Microsoft doesn't know what it is. And so you may be one of the first few who've run version 4.4. So you can just, instead of telling it to close, you can override that warning message. And so if you've got this up, now what we're going to do is in the File button, open and browse to the location that you have just exported that HMS directory to. So I put it in, let's see, WMS, HEC-HMS, class, export. Okay, and there it is. Okay, so select that, and it gives us a little complaint that WMS exported it into version 4.2, and now the program's on version 4.4, but it can make the conversion. That's fine. Make the conversion. Alright, so it doesn't show us anything on the screen to begin with, but if we use this window over on the left, we can explore a little bit and double check that the things that we just set up in WMS have been imported the way we'd expect. And so for the models, you can see it gives you a schematic that is in some ways similar to what we would see when we opened up the hydrologic modeling module in WMS. I mean, when we did that in WMS, we'd always have the DEM and the outline of the watershed in the background, but what this is showing us is it's showing a watershed connected to an outlet. So here's the watershed, and it's connected to an outlet. So that's the watershed. In the meteorological model, we can look and see that when you expand that out, we have our type 2 storm, 3.74 inches, and so it did carry over the rainfall data. In the control specifications, it knows that the simulation is going to start on the 17th of April at noon, finish the 18th of April at noon in 15-minute increments. So those were the three components that we'd set up. And what we can do now is we can execute a model run. So we're going to create a compute. So here in compute, create a simulation run, and we're going to call it run 2. It may have by default already set up a run, but let's actually, no, let's not do that. Yeah, okay. Rather than creating a new run, WMS had set up the first run that we want to do. So just in this drop-down box, select run 1, and then this compute all elements. Click that. Okay, it's just run what we had set up in WMS, and then we can see the output for it in results. So global summary table. All right, 190 CFS. I kind of forgot what we had over here. So what did we have for this HEC-1 model? It was saying 192 CFS. So it's essentially the same. 191 CFS, you know, if you round up from 190.5. So you're getting the same answer. It's just that this, what we're looking at right now, HEC-HMS, is the Hydrologic Engineering Center's answer to the fact that they didn't have their own native GUI. They didn't have a graphical user interface for their hydrology model. And you know, Aquaveo's software, WMS, it's paid software, whereas this is free. So free gets you HEC-HMS, paid gets you WMS. There's relative advantages and disadvantages of each, but even if by mandate you have to be setting up a HEC-HMS model, you can still use WMS as the tool for setting it up. Now, we're running low on time. It's 9:49, so we don't have time to show you, but WMS could read back in the solution. So what we just ran, this model that we just ran in HEC-HMS, it created some output files that WMS itself can read in. And so if we just look at the solution, here's a solution and an output file. So this is basically the answer to the model that we just ran, and WMS can read that in, but we won't go through the trouble. That just, I wanted you to see the last of the models. You know, we talked about the rational method, national streamflow statistics, TR55, HEC-1, and now HEC-HMS. And so that's 5 models that we've been through with WMS. Any questions about what we've done today before we finish? Okay, well, I'd encourage you to be working on homework 11, and if you have any questions on that, let me know. Otherwise, I will see you in class on Wednesday. Hope you have a good day. Bye-bye.